Hello and welcome to Hyperstition number 18, Radical AI and AI Accelerated Material Science. Not just material science, but AI Accelerated Metallurgy. Material science is pretty foundational to any area of engineering endeavor. If you look at like the maximum speed that a jet engine can travel at, it's limited by its thermal properties until the metal melts. If you look at the heat dissipation in a computer, it's a fundamental property of the silicon, transistor chemistry. Every single aspect of our built economy depends on the quality of the materials we can engineer. And the space of possible materials is absolutely gargantuan. It is beyond reckoning. And so to speed run this space, to develop super alloys, the Reardon steel of the future, we're going to use AI, and not just AI, but robotics. And so a hot startup in New York City led by Joseph Kraus is our guest today. So hello, Joseph. How you doing?
Doing good, man. Good to see you, Andrew. Happy to be here.
Yeah, man. Thanks for joining. So I'm curious, what is Radical AI? What are you guys building?
So what we're doing in the simplest of forms is building AGI for science. And we're using that to remove materials as the biggest bottleneck to our most important industries. That is what we do as a company.
Okay, that's pretty succinct. Now, how do you actually do that?
That is not succinct.
Yeah.
This is the conversation I'm looking forward to have. So, look, I think the place I always like to start is why materials are important, and then what is this future science that you're going to build, and why is materials relevant. And I always take a step back and paint this picture on how many industries are really impacted by material science, right? You just talked about jet turbines, a great one, automotive, aerospace, manufacturing, defense, climate, energy, semiconductors, electronics. The most important industries in the world are all a direct result from materials R&D. But you look into the materials industry that we have today, and you constantly see the same problems. Incredibly slow timeline, right? Like to go from discovery to manufacturing, 25, in some cases 50-year process, and we're still using materials of the 50, 100 years ago today. Ridiculous cost because of that time, from 100 million and onward for a single system. And it's unbelievably fragmented. The people who do discovery aren't the people who test the materials, who aren't the people who manufacture and sell them. And so there is so little, I should say, lack of continuity between the market that we just don't field innovation as fast as we do in other spaces today. And that's a problem because materials drive all of them. And because it's such a large market and it's imperative to building the world that we want to live in, that is a really important problem to solve. That's what Radical is doing. And so when you ask how we do that, our approach is around solving those specific problems, and very specifically bridging the gap from discovery all the way through to manufacturability and selling raw materials. And we actually want to take our AI scientists, so our intelligence layer of science and materials, and connect those two things together, going from the lab into testing, into manufacturing, and cycling that data all the way back to discovery so that you can truly go through that entire process in months, maybe a year, versus the 25, 50 years it takes today. That is the way that we do that. And we'll get into what does AI mean, what do robotics mean, and of course we'll cover all that. But at a high level, this materials flywheel is the way to shorten that gap.
Totally. And I think to put meat on the bones on that, like development time, commercialization process. I mean, my last industry was nuclear fusion. The discovery of high temperature superconductivity was like 1987, and it wasn't until like the mid 2010s it had been packaged into a format that could even start to be produced commercially. And now that's the entire basis for the modern nuclear fusion industry is the ability to produce HTS tape at scale. And that took like 35, 40 years.
And even nuclear is a great example. We do a lot of work in nuclear fusion today. I'm really excited about that industry. When you talk to nuclear companies, there are so many problems that the industry is not solving and is actually forced, as you know better than I do, to use materials from other industries, whether it's aerospace or automotive or even just a different industry altogether. They have to use existing technologies and materials to try to build this fusion reactor. and they don't scale or they don't work. A perfect one's the diverter, right? Diverter is a super important part in the reactor design. Mostly tungsten today, given its melting temperature and ability to withstand radiation. But even there, usually coated. If it's not coated, if a lot of defects, a lot of grain boundaries, a lot of cracking and brittleness that can form. If you're building $1 billion reactor, like those are not okay properties. You can't have that stuff. You need to get rid of it. The perfect area high entropy alloys are actually well suited for. We call this extreme environments. A lot of stuff we do is in extreme environments. The perfect one where we're looking at high entropy alloys for diverter or front wall facing type material inside reactors. So industries like that, they require novel materials to move faster and to innovate. Without them, a long road to use the things of the past and the things of the future. It's never worked that way, and it will be a continued struggle to continue to do so.
Mm-hmm. Well, then, so how do we sort of, put our like pragmatic engineering hats on and kind of approach this problem from the ground up? Like, how do we get traction in this new material science?
Yeah, so I think the first thing, and this will go into kind of like the platform approach that we like to build. And I can actually flip over here real quick. So in materials, what we really view the future as is what a gentleman by the name of Charles Kuhlman, who is the VP of materials at SpaceX and Tesla, coined. To my knowledge, he coined, which is concurrent engineering. And if you look at so many other industries, even in materials like polymers, for example, so much of the materials we make are in direct response to an engineering need. So, hey, we need this part, this component, this whatever. How do we actually make the materials that can solve that or give us the performance that can meet that spec? But in something like alloys, so aerospace, defense, automotive, we don't do that. The alloys that we use today in the space industry, and I'll come back to this, they're really old. They're from like the 60s that we're actually using C103, Inconel 718, TZM, etc. In the 80s, we figured out to put carbons on them to pretty much push super high temp survivability. We haven't really innovated since there. And so this concurrent engineering approach where you no longer use materials of the past. Rather, you make an engineering spec. You start working on the materials that can meet that spec. You see new properties on those materials, and then you actually come back and update your engineering spec. Going back and forth, or as in the phrase says, concurrently engineering a new product, that is the future that we see. And what Radical believes in building is a flywheel that can become a platform, and not a platform that we can sell, but as you're seeing on the screen, one that we can use internally to develop the new materials of the future. And I just talked about alloys, that top bucket there. That's where we're starting. We're in alloys today. We can do a deep dive into alloys if you're interested. But this idea of starting with the material demand, doing discovery and the process development simultaneously, and then in turn being able to go to the end industries like defense, like energy, like automotive, like electronics, and concurrently in engineering back and forth between what are the materials that we need to meet the engineering specs that you're going after. That's where materials needs to go. And that is not the place materials are today. To us, that is the $100 billion company. Like that is the way we build civilization on Mars or the moon. Think about rad hardened chips for space. Think about superconductors and floating trains and lossless energy transmission. Thinking about fusion and any other industry you're interested in, right? It doesn't need to be those. But there's no way in 2050, 2060, 2070, we're still using the alloys of the 60s to build our moon and our Mars colony. I refuse to believe that. And so this concurrent engineering approach, I think, is how we get there. What Radical is building is the platform to try to exhibit that.
And just in kind of like rephrasing in my own words, like this concurrent engineering, essentially that it's the materials sort of formulation, synthesis, but then also packaging and performance is done sort of simultaneously. So you don't get to this position where it's like, oh, there's this wonderful material, but we couldn't produce it in a high purity yield or package it correctly. And so we had to go back to square one. Instead, it's like by the time we finish this, we know that it works in its use case. Yeah,
you're exactly right. And this is that fragmentation I mentioned. Like if you work in alloys, when you talk to metallurgists and a lot of the alloy companies that exist today, This will be the first question that they ask. And by the way, it's for good reason. So in alloys, and there's a little bit of a science detour. We can back out of this, of course, but a lot of the mechanical properties that you're targeting are really based on microstructure. So grains and phases and what's going on in that microstructure is really indicative of the end properties that you're going to see. And so industry naturally is worried about discovery because microstructure can change when you go to large scale. It is not always the same as it is in the discovery lab and when you use a VIM or a VAR or additive process at large scale. But that is, again, under the constraint that it takes 10 years to make the new discovery and then another 15 years to think about how to optimize the formula, the recipe to make it at scale. Well, when you bring AI and autonomy to that process, we're targeting 100 alloys per day. That's 33,000 per year. Remember, robots work 24/7. They don't take weekends off. You're doing more materials. You're doing more alloys discovery in a year than arguably has probably ever been pushed in a certain field, like a high entropy field, for example, not at large, but in a specific field. That's a stepwise change in discovery. And then more importantly, you're not doing those with humans. You're doing them with robots and with AI. And so every experiment you run, every single process parameter in that experiment, temperature, pressure, oxidation, concentration, humidity in the room, I sneeze on the sample, I knock a beaker over, it doesn't matter. All of that data is captured. It's analyzed autonomously and it's fed back into the scientist, the AI, that's predicting the material in the first place. And so you have this trove of information on what are the temperature ranges that you're going to go to large scale processing with. What about pressure? How have we seen microstructure change over temperature ranges and whatever, all the other properties that you want to attempt and exhibit. That is the fluidity that you need between discovery and manufacturability. And that just doesn't happen today. And so I think to your point, being able to go all the way into end property and make materials that have the same properties there as they do at the discovery stage doesn't happen today. And there's a huge opportunity in being able to do that.
Let's nerd out on this alloys for a second, because I'm just a curious guy. How do we actually go from microstructure to alloy performance? Like, is there some intuition there? I mean, that's like a PhD topic, right? But it's like
that is a PhD topic.
Yeah.
So good question. And I will caveat this, of course, with I didn't do my PhD, my work in alloy or metallurgy, but I know enough now with us moving into this to be dangerous. So the microstructure itself is where you start to see the impact on the end properties like ductility, like CTE, thermal expansion, like yield strength or oxidation resistance, etc. And so for a perfect example, a lot of the high entropy alloys that have really high temp performance and really strong oxidation performance historically have been single phase alloys, body centered cubic, single phase. And you see single phase other places. You've probably heard in turbines, like the single phase materials that are produced there. You just don't have this ability to introduce defects and cracks and propagation and a lot of the mechanical properties of materials. My advisor in grad school taught that course, so I hope he's not watching this because he's going to be like, you should know more about crack propagation. Really impact those end properties that you can have. And you can also use them to your advantage. There's been a lot of work in, I would say, not the high entropy field, normal metallurgy field, where things like interstitials or nanoparticles are really important strengthening mechanisms. They can provide a pathway to essentially move or be a kind of a local defect that can absorb things so that it is more ductile, right? Versus being super brittle. And again, that's the extent of it. I'm sure a metallurgist could go very deep into the movement of electrons and the DFT behind like why those things are happening. And I can't do that, but this is why these things are so related. And so when you're studying microstructure, phases are important. Grains are very important, grain size. And, as you move to different manufacturing techniques, grain size changes. And that changing in grain size can change microstructure, which can therefore change mechanical property. And so when you're putting something on the front of a hypersonic missile and you're looking for the perfect ductility, CTE, emissivity, melting temp. They're like, so temp that you can withstand temperature at, and you don't want to oxidize. If you start messing with that microstructure when you go to a larger scale and you lose 50% performance in oxidation, that alloy is going to erode in mid-flight and it's going to blow up midair. That's an unacceptable tolerance that's there. It's even more felt in aerospace. Creep and fatigue. Creep and fatigue are like the mechanical test that aerospace engineers need to do, rightly so. Along, longevity of an alloy performance, creep and fatigue, those things change a lot over time as you add stress, as you add pressure, as you add temperature, as you really work the material over a period of time. In alloy processing, we work the material already. We actually use heat. We use pressure. In the additive approach, they do this process called a HIP, which essentially allows you to harden or strengthen that material, better word than harden. So all of that is very, very important to end property. And this is why, if you go talk to an aerospace engineer, they get very nervous about an alloy showing really good tensile properties, stress, strength curve, or stress strain curve, or like a oxidation result in a button size, because they think that grain structure, that microstructure, that grain size, that microstructure is going to change when you go to large scale, and those properties might not withstand there. Does that make sense?
Yeah. I'm trying to also remember my materials course. So I think creep is like the ability for over time deformations in the crystal lattice to slide across each other. So it kind of has this slow movement. And fatigue is like the accumulation of these dislocations that I think it's similar to I guess work hardening, where it has an apparent increase in the Young's modulus, so it seems stiffer, but it actually becomes more brittle. So it's its yield strength decreases, I guess.
And remember, this is exactly correct. And some of these materials have really exotic behavior. High entropy is a perfect example. At room temperature, for a lot of them, super brittle. When we try to process some of our alloys, they just shatter instantaneously. When you try to do normal, cut out a tensile bar that you want to do a tensile test with, completely shatter. When you heat them up, great ductility, not that brittle at all. And these two are, of course, inversely proportional, but that's important. And so what we've had to go do, for example, that we didn't think about when we started making them was, well, now we need to study the relationship to temperature. And we need to actually see where we start to see this brittle to ductile transition under certain temperature. That's very important for processing. Again, when you're casting alloys or you're using additive manufacturing techniques, powder metallurgy, powder bed fusion, DED, pick your technique. That's a very important amount of information to know. And because you're working with alloys and elements, all this chemistry starts becoming involved. Oxidation and parts per million ppms of oxygen in your precursor and your resulting alloy, very indicative of performance. Immensely important to track. We must keep samples below 100 ppm. Really below 50 ppm is ideal. If we see any variation, we see direct variation in mechanical performance of alloys. And that comes into the processing technique you used, which comes from the temperature ranges that you're pushing in, which is coming from trying to get at this dislocation problem that you mentioned on work hardening.
Yeah.
The microstructure is such a complicated science that it's so hard to control. All the variables of the recipe are very hard to control. That's why when you go to manufacture, it takes 15 years. You have to go through all that individually and irrespective of the discovery pathway.
Help us understand too. You said this a few times. High entropy alloy. What does that mean? Is this? Is there a common example we would know, or is this a pretty new category?
So it's a new category in that people are trying to produce them at large scale. High entropy alloys themselves are not new. They've been around they've been the holy grail of metallurgy for the last probably two decades or so. We just can't make them at large scale. And so they haven't been felt by the industry yet. It reminds me a lot of graphene. If you've been around graphene, like amazing material. I use graphene every day in the lab. And the semiconductor industry will laugh if you say they're going to put graphene in something, or other industries. So they've been very much that. And they're alloys that have from 5 to 7 elements in them that are close to equiatomic, or they're supposed to be in nature. In reality, they actually kind of aren't directly equal, but you see typically between 25 and 35% weight percent of an element in said alloy. And that is this makes up this high entropy camp. And what they're so exciting for is their performance in extreme environments. They have very high melting temperatures, pushing 35, 4,000 degrees C. So I don't know what 7,000 or 7 and change in Fahrenheit probably or similar. So super high. Amazing resistance to oxidation and or corrosive environments like neutrons, for example, in a nuclear reactor. That's where they're most exciting. They have really nice strength as well. They are good. They're strong materials. We have seen Vickers hardness measurements, which we do with a micro indentation tool, over 1,000 actually, like over 1,100 in some of our cases, which were some of the higher measured Vickers hardness alloys that we've seen. So they just have all these amazing properties that you can think about: a rocket, a hypersonic, a nuclear fusion reactor, super hot, a lot of pressure, a lot of oxidation and or corrosion in the environment. And you really need good performance, right? You don't want them to bend when they get really hot. You don't want them to also be too brittle and shatter when they start feeling different pressures. So they're just these alloys that, really put simply, can have really cool properties in really crazy environments. That's the best way I like to describe them.
Right. So we have so just like for comparison, like turbine blades, it's like single crystal nickel or very low impurity, like a pure block of copper. There's just one kind of cubic lattice. Next step up is like some kind of dopant. There's like an interstitial addition, but it's percentage-wise a low by weight or volume. High entropy, it's like almost equal mixtures of different elements all together at the same time.
Correct.
But that's like way harder to produce to get that consistently. And also, like, how do you even anticipate or design the material properties? Because really, probably you start with like, we want these desired performance metrics.
Right.
How do we go from that back to what the initial formulation of the alloy is?
This is a really important question. This is so important that we think a lot about the data that we can actually capture in the lab that can actually help and try to inform that. And we have bought tools and put them in the lab that start to answer that question. Now, you're not going to answer it entirely, because at the end of the day, you need to go produce it at 10,000 pound, 30,000 pound sizes so that you can machine and manufacture them for, again, turbine or nozzle, rocket engine nozzle, etc. But still, it's very hard to connect those things together. Like, there's not a big data moat there. There is no captured data there, by the way. Like, if you call the alloy producers, Carpenter, ATI, etc., they'll get mad if I say this, but I don't care because we're competing with them. Is they don't have the data. You know, they capture like 5% of their data for quality assurance and control. They're not tracking all the mistakes that they've made over their 30, 40, 50 years in research in a certain area. And so that's just completely sitting in a warehouse somewhere, or even worse, like a scientist's brain. And this is a problem for science generally. We work on high entropy alloys. The United States Air Force, the research lab there, AFRL, works on high entropy alloys. We have a full disclosure, a grant from AFRL to work on high entropy alloys for hypersonics. I want to make sure I disclose that. I have no idea what AFRL has done in hypersonics and HEAs, and they have no idea, before we started working together, what we have done. Why? Why does that exist in inorganic science today? That's rather than stand on each other's shoulders and constantly compound and build to the end solution, we probably repeat the same experiments that don't work for years that someone else has already tried and done. That is where the most rich information is. Like, yeah, we read publications. Like, yeah, we pull in all the data.
Yeah.
It's really the negative results that are the most interesting. That is scientific intuition. And so to get back to your question, how do you think about processing and connecting it to property? Usually the answer to that question is a person who's been in the fab or in the manufacturing facility for 25 years and sets the dial to 3 and then says, don't touch it. And you're like, why? Like, why? And he said, just, I know that's where it goes and don't touch it. And of course I'm using an alliteration there, but I have an advisor who was at 3M for 25 years who said that is exactly the way it is in manufacturing materials. We're trying to break that exact mold and the connection between them.
So get out of this almost like alchemy / ritual, like, you know,
Yes.
where it's like this has
Yeah.
been passed down for decades, don't mess with it, to actually like, no, that's why those settings work, but if you approached it from this different way, you would get a completely better result.
Correct. And then you could use those settings to your benefit. Like if we could have those settings and we knew that you had to be at a certain temperature or a certain pressure or certain concentration. And again, oxygen in the room. You have to be under vacuum because the oxygen, the ppm that starts to form in these precursors kills mechanical properties at this certain scale. Now you can take all of that and you can actually bring it into your design engine. And I think I actually have something in here. So like here's the way that the AI scientist works, right? And what you see on the left is just an example of 5 different things that we're taking into the different AI scientists in the middle. We can run up to 100 agents concurrently right now. That is pulling in information though. And so you see thermocalc, which is CalFab, which is a big alloys database, the literature index. We use atomistic models, typically graph neural nets, what are called machine learned interatomic potentials, allow you to do DFT very fast. Using Bayesian optimization to think about optimizing in large search spaces, which I'll show you that slide in a second. High entropy alloys are a very large search space. But then most importantly is experimental data on the right hand here. And so you actually have the characterization of your materials, the properties you're testing, and even human analysis. I tweeted this a couple of days ago because we get asked all the time, now that our lab is almost fully autonomous. There's one tool of 11 tools that's not yet autonomous. So it's still human driven, but all the rest are autonomous. Do you have humans in the lab? And the answer to that is absolutely. Actually, we have scientists still labeling the data just so the AI scientists can learn how they're going to label it and are watching their intuition and absorbing that. I have PhD metallurgist here who will say, I just had to melt the right side of that alloy a little bit longer. It didn't feel homogenized. What does that mean? What does that mean? When you go to reproduce that experiment, what does it mean? I had to melt the right side a little bit more. First of all, that's not direct, because it wasn't homogenized. What is homogenized? How can you tell what's homogenized? At what point are you satisfied that it has homogeneity? These are very hard questions that don't come from scientific literature. They don't come from computational data sets. They come from experiments and they come from intuition. Mm-hmm. You need to capture that. And so our AI scientist, this yellow box in the middle here, this is capturing and pulling in all of this information as it thinks about making something new. And so why am I saying this? Well, bringing it way back to the question you asked a couple minutes ago. If I could add a couple boxes on this screen that were the processing conditions of alloys at scale, that would be another lever, another point of data that the scientist can bring in real data, raw data, but also intuition. That 25-year person that sets that dial at 3, what does that mean? Why do you do that? What is the resulting property that you look for because of that? Can I learn that as an AI scientist? That is the piece that no one has captured yet. And that is where we see the value.
Yeah. And that intuition thing, like scientists and engineers often can't even give you a straight account of why. It's just, I just had a feeling, right? Yeah. So I guess the question is kind of funny, but like, given that we don't really have good mechanistic interpretability of what's even going on inside an AI model, we don't even need to actually solve the hard problem necessarily of like, how precisely does a certain initial formulation get a desired material endpoint? It's sort of so long as we can get there in a consistent fashion, like it's kind of abstracted away.
Correct. One thing I like to say, and on interpretability, shout out to the Good Fire team. Erico is a good friend. They're doing incredible work. If you're not following Good Fire, check out their work in science on interpretability. What we like to say, and this is gonna, if there's any physicists on this, get ready. Is there a world where you can get rid of multi-scale modeling or DFT, right? And that's an aggressive claim. That's like, hold on, the entire industry's been built off that over the last 30 years. What do you mean? I don't mean this year. I don't mean next year. I can explain what I mean. Right now, the most important things in our discovery loop are the properties that our alloy has and the composition of that alloy or how to make it. I actually don't care what the microstructure is. I do for all the reasons I just walked you through, and I'll come to that in 1 second. I'm talking about the discovery side. I'm talking about you have 10 to the 40 different potential combinations of things you can make. Where do you start to screen? Start to screen on properties and then the resulting compositions that will exhibit those properties. I don't need to worry about the multi-scale physics there. I don't need to worry about DFT. If I made it in the lab and characterized it, do I actually need to understand if it's on the convex hull with DFT? I mean, maybe, and yeah, then you can get into like if you want to go into like electronic properties and band gap. I know, I know DFT is used, but you don't to screen. And so we have this view where generative models, and it'd be even cooler if you could do interpretability with said generative models. If you can just, turn a dial on a certain property spec, ductility or CTE or oxidation, and you're watching as you're moving this oxidation bar, more resistant to oxidation, less resistance to oxidation. You're watching the structure like start to change its weight percentage in tungsten and niobium and whatever else is in there. Then that speed of iteration gets immensely powerful. You go from 10 to the 40 in a search space to probably like a couple thousand. Well, when you're building A labs, I just told you I can do 33,000, or we'll be able to do 33,000 per year. A couple thousand is great. I can make all of them. I can characterize all of them. I can test all of them. And then I can do multi-scale physics. Then I can run confirmatory DFT. And of course, bring in the quantum chemistry that you should do to have analytical, rigor-based materials design and discovery. But I think it's a mistake to put so much of that up front. But when you don't have generative technology that can do what I just described, well, then you start with simulation. You run DFT and you see what structures, what compositions exist on the convex hull. And out of those, you try to run some MD and see if you can predict properties over a long enough length scale. And then you take those to the lab and you try to make those things. And you do this serial experimental process or scientific process, from computational to experimental, when AI allows you to do it in parallel. You can do all of those things simultaneously. That is the power of AI-driven discovery. And that's the technology that Radical is building today.
And I feel like that makes me think of two things. Like one, like the computational cost of doing a direct DFT simulation via an ML inference is like about 1 million times higher probably. But also, starting with the DFT or quantum chemistry simulations, you've already bounded the solution space.
That's right.
Beforehand. And so it's like, as the model and data size gets bigger and bigger, we need to pre-process the data less and less until it's just,
phenomenal point. So this is a cool slide I love showing. So if you look on the left-hand side here, this is like the currently explored alloy space today with these elements. And you can see all the literature dots that are there. And then you can see like where our scientist went, right? Like over here, and these yellow, and then down here by molybdenum.
Let's make this bigger.
Why did it go there? Like, how come humans never went there? And how did the AI know how to go there?
Yeah.
And that is what you just mentioned, which is humans naturally have error. They naturally bound themselves to the things they know. Look at all the alloys up in this space. You got like a few fringe alloys down here. And I think what's really cool is this slide right here, which is, this is from scientific literature, by the way. So there might be more, but if you use scientific literature as your data set, there have been 3,425 high entropy alloys ever experimentally validated. In 3 months, we've done 250 experimentally validated. That's the power of AI. That is the getting outside your normal search space, right? You're not putting the confines on up front to what you just said on the DFT example. You're going way past that. You're backing out and you're understanding, how do I discover new things? And that's the most exciting thing in the world to me. That flywheel, that's why we think this is a $100 billion company. It's not in alloys. Alloys are probably like a $10 billion market today. If you use public comps, it's all the other systems that you can move into when you take said flywheel. I'll go back to when you take said flywheel and you put this out across a multitude of different industries. Now you
Mhm.
solve material problems in short timelines across a lot versus one. That is how you make the materials of the future. That is how you get the RTAP superconductors. That's how you get the high entropy alloys. That's how you get to whatever other material tickles your fancy. Like that is the future of scientific discovery. And like I said at the beginning of the call, that removes materials as the biggest bottleneck to our most important industries. That is the mission statement of the company.
That's awesome. And I mean, like, just like you need thousands of miles for self-driving cars, like
Yep.
you need your own platform that is producing thousands of experiments.
Correct.
I'm curious if you can like dig into like what is the, I guess, physical embodiment of the, like, I guess the testing robotic side, because
Sure.
the AI part is probably people are more familiar with. Oh, of course, like AI can do all this stuff, but like
Yep.
for you guys, like you have to have your own sort of fleet learning like internally.
Correct. I love the self-driving example that you just gave. One thing we always like to talk about, a quick differentiation or important clarification in the space. You see a lot of people talking about autonomous labs, and autonomous labs are really important. They were the first step in this field. My co-founder, Dr. Herd Cedar from Berkeley, built one of the original ones called A Lab at UCB and Berkeley National Lab. It's an amazing A Lab. But we're not just building A labs, we're building self-driving labs. And I always compare the difference to like, hands-free driving versus self-driving, a Waymo. Ford Blue Cruise can keep you in your lane and make sure and like turn for you when you put the turn signal on. In a Waymo, you can close your eyes and take a nap in the back seat and end up at your destination. You don't know what turns it took, what speed it went, where it had to divert or detour because of a road obstacle or anything that happened in between. You know where you started and where you ended. That is a self-driving lab. A lot of the A labs today are that Ford Blue Cruise. Yeah, I can change lanes for you. I can hold your speed. I can alert if there's a car stopped in front and slam on the brakes. But you need to be paying attention to the road, and you need to tell me when to turn left and tell me when to turn right. We want to take that onus from the scientist, and we actually want to put it to the AI. And what that does is it allows 10 scientists working on one problem today to having one scientist working on 10 problems at a time. Like I always tell the team that we're going to be able to send a scientist to the beach in the Bahamas with an iPad, and they're going to like run 100 experiments. I'm doing a bunch of research today. I'm just sitting on the beach. We're almost there. We're not there yet. We're very close to being able to do that today. And I think that's the really important piece around self-driving architecture. And so now to get to your question, I think it's important to preamble with that, by the way, because I think, again, self-driving means different things than just making something do experiments fast. So now to your question, the robotics and the integration. Number one, self-driving labs are unbelievably hard to build because of the interdisciplinary nature. Mechanical engineering, mechatronics engineering, material science, materials engineering, robotics, the machine learning and AI side of this, all the way through to software engineering. Like the backend, we have a backend infrastructure called Antimatter that runs our entire A lab. A lot of different technical teams smashing together on a single idea to make that become a reality. Number two, none of the industry is there yet. Every material tool that we buy looks at us like we're crazy when we say we're going to automate it. In some cases, they fight us against automating it. We have had tool vendors not give us access to the software on the tool. Straight up said no. We've had to negotiate and like finally got access. Barely any of them have APIs or SDKs or whatever you need. And the ones that do, they like lock down the data analysis. So like they'll let you pull or like run the tool and like understand like the state of the tool, but they won't give you the XRD spectra and let you mess with that. And we have to pay for that and constantly work with them to get that as well. So the infrastructure is not built for self-driving. It's built for human-driven science, and that's a change. And then number three is the capture, data capture. The human brain is very smart, as we all know. Nothing new there. Scientists will naturally observe and record things throughout their scientific and experimental process that never gets recorded, but is very important to the discovery. Right? I might always when I did a bunch of semiconductor work in my PhD, so I was working on these neuromorphic chips, and so we used e-beam lithography where we would pattern very small transistors, and we would use 2D materials, transition metal dichalconides, to make our semiconductor circuit. I would always put an extra 15 seconds on the resist layer because I'd want like just a little bit of a thinner coating on PMMA A4 or the A9 or whatever I was using at the time. And it was almost like, I don't have a superstition, but it was almost like I just like doing that extra 15. I always go past the minute that we say to do by 15 seconds. Where is that captured? Right here. Not repeatable. That really doesn't even show up in publications sometimes. Like people just, we do it for a minute and change, or we do it for, around 90 seconds or whatever it might be. You have to capture that. How do you know to capture that? What does that mean? And that's a simple example, by the way. That's time. So time is a number. You can capture it. What about the example on the alloys I gave you? When I'm casting, when I am melting down my precursors, I am making a decision on when I believe the liquefied metal is homogenized enough to form an alloy. That's pretty ambiguous. That's not binary at all. Determine that. You need the AI scientist to be able to make that decision. To make the decision, I think it's homogenized enough. I think it's good to go. I think the left side of that, of the little crucible that we're mixing the alloy in, I think the left side is not melted enough. It feels like there are flakes of tungsten in there. And I know it's tungsten and not copper or niobium or aluminum flaking or any other million processes that can go wrong when you're blasting alloys with a plasma torch at 3,000 degrees Celsius. That's intuition. Like that is this arbitrary, non-binary process and experimental discovery. That is the third hardest part of A Labs, where you need to build a scientist that can take that in. And we just released open source. If you haven't read this paper, for everyone watching, definitely read this paper. It's incredible work. A vision language model. There's a blog on our website. You can find the link to archive there. On the materials world's first vision language model, because we were taking in SEM, XRD, hardness tests, and we needed to analyze what was the microstructure doing? What were the grains that we were seeing? What were the dendritic formations on the top of the alloy? So we had to build a VLM to do that. It didn't even exist in the space today for materials specifically. So those are like some of the examples of in a self-driving lab. When we say self-driving lab, it's much more than high throughput experimentation. It is the combination of the three things I just mentioned to you that have to work in complete concert, that can't mess up the science, that have to be very fast, and have to be a part of this interconnected active learning loop to do new discovery. They're hard to build.
Yeah. And just for people listening, so SEM, scanning electron microscopy, and XRD is X-ray diffraction. X-ray. Yeah. Right. So graph-based neural networks, very good at capturing kind of interatomic potential information, could supplement or replace the DFT part. On the self-driving lab, is that more of a Bayesian optimization? That's like a real-time update design of experiments, like
right now,
based on the last.
That's correct. On the vision stuff, we'll look at computer vision a lot. Open source, like computer vision models, we don't build those from scratch. We have looked into LLMs for crystal structure prediction. And we have a lot of work in diffusion, as well as using some of the open source diffusion work as well. MatterGen from Microsoft, for example, great team over there. Tion, great researcher. Just left Microsoft Research this week, actually. But wide range of technology. BASOP, though, in the lab per se, like in the design of it, we call it design of experiments loop, was the place that we started. Yes.
It sounds like, I mean, there's just massive tailwinds here, right? Like
Agreed.
Robotics are only getting cheaper and better, more general purpose, right? The fundamental model architecture is getting better over time. Our ability to deploy these at scale and train these things, like, are those the two biggest sort of why now type questions or answers?
That's a great question, Andrew. They are a part of the answer. Absolutely. They are incredibly important. We can build self-driving labs today and have the AI technology today to build that closed loop. Absolutely. There's a third one that's really interesting. I found myself in DC a lot more than I thought I was going to when I started the company this early on, which is we have reached a point, in my opinion, in technology where we cannot reach the next level, cannot ascend the Kardashev scale for those physicists that like to go deep without new materials. And I equate it a lot to the beginning of Silicon Valley and the space race. And I think people forget. I love when VCs are like, "Oh, hardware is scary." I'm like, "You literally live in Silicon Valley. Like it's literally named after Silicon." Space race. We need chips. DARPA comes along. We're going to fund things. Fab 8, Trace 8, roll out. Shockey to Intel, to the whole forming of Silicon Valley as we know it, as one piece of that. And then from that technology, fast forward 25 years, 35 years, all the way to Uber, Airbnb, Figma, pick your biggest, whatever your favorite company. Very hard to envision those in 1960, 1940. Not because it was impossible to visit calling a car. No, I think taxis probably existed in New York. I don't know for sure, but I'm guessing they did. Because it was impossible to think that you would have enough compute in this to be able to build something like that could call a car from anywhere in the place you're standing and bring you to the place you're going. What does that mean 50 years from now? What's the version of that? And it feels like in so many areas of technology, semiconductors, energy storage, space, aero, defense, oil, gas, energy at large, like all the way into like catalyst and sustainable aviation fuel and like you name it. We've bumped into the ceiling with the existing materials we have today. I don't know where else we can go with materials. Like in semiconductors, this is already happening. We're out of nanometers, right? 2 nanometers are already fake. Like as in like the distinction is fake. And now we're looking at 3D stacking, heterogeneous 3D structures. Very cool. I think it's gonna be really cool in semis. But what comes next? And I think that is what is so important about building this technology and focusing it on connecting discovery to application. Is that we really believe this third tailwind will require novel materials advancement. You could make the argument that 10 years ago, it wasn't required. I'd obviously disagree with you. There were obviously material advancements 10 years ago. I'm not saying that. I'm saying that maybe more optimization. Actually, if you go to aerospace, not technically 10 years ago, to be honest, like not really. I would make the argument that if you're going to build a moon base, Mars, new materials or it won't happen. Fusion, new materials or it won't happen. Hypersonics, new materials or it won't happen. Reentry, reusability and reentry, new materials or it's not going to happen. I don't know. In-memory compute, neuromorphic compute, scaled quantum compute, new materials or it's not going to happen. I just think there are energy, perovskite, solar. We already talked about nuclear, even things like thinking about storage, battery chemistries. Even, of course, been a topic for the last 10 years, but even there, still room to go. I just don't see a world where you're not going to make new materials to make those things become a reality. I see the world that is on the screen right now, which is this world that you are using really interesting material design and retrofitting it to the new applications you're trying to build today, like a Starship coming back into atmosphere and facing extreme temperatures and needing a heat shield to deflect against that. Now, Elon said this, right? The biggest risk to Mars is the freaking reusable heat shield. And by the way, they deserve the credit. I talked about concurrent engineering earlier. I should have said this then. Charles does this. SpaceX has alloys they've developed internally with concurrent engineering to solve some of their bottlenecks and problems they faced it with industry-based alloys today. That exists. They have them today. One, I love using them as a proxy of where the world's going. They're quite good at picking that out. But two, tip of the iceberg. I think everything that's coming in the next 50 years will require novel material advancement. And then that begs the question, well, then whoever has the scientific brain, whoever replicates AGI for science will be at the forefront of capturing that.
Yeah. That actually makes me think that the 10 billion alloy market size is actually an underestimate. Right. That's the market demand for alloys with their current performance characteristics.
That's correct. That's exactly right.
Right. So like the elastic demand curve for a higher performing, high temperature, high entropy alloy is actually extremely like fast. Like if you could get something 10% better, we would build 1,000 times more or something.
I completely agree. And then you can get even more granular than that, Andrew, supply chain. So like a lot of the alloys today, C103, I think it's like 10%, give or take. Someone can fact check that. Hafnium. China owns a majority of hafnium. Massive problem for the US and DOW, DOE. Everyone wants to move off hafnium. You could make an alloy with the exact same properties as C103 or like similar properties as C103, but remove the hafnium and have a massive market sitting in front of you. And that's not even that's not pushing performance. That's not enabling the things you just mentioned, right? And I think even the technology we're talking about today, rad hardening chips. How do you think we're going to rad harden chips? Materials. The material science is going to rad hard chips. Energy generation in space, with if you guys haven't listened to that Elon Cheeky Pints podcast yet, that one was awesome. That was electric. Material science, in my opinion, driving the efficiency curve of solar-based systems, whether that's perovskites or something else. I don't know. I'm not a solar engineer and I haven't spent time in that space, but I know it comes back to materials. So when we tell people we think this is a multi-trillion-dollar opportunity, we actually believe that. Like we think over the next 50 years, that will be the case. We actually genuinely believe in 50 years, a company who can make these materials and scale them can be worth $1 trillion. We believe that. And that's the whole, that's one of the huge areas that is important is if you want to build this world, that's the whole point of doing it. Like if you don't want to build the world, well, then you're probably like, that's too hard. Like, screw that. Like everything Joseph talked about today, I am out, dude. I'm like, this is way too hard. But if you want to be a spacefaring civilization, and as Elon tells me, we're not even going to be the ones controlling it, then you're going to need materials to do that. And we want to be the company that can do that. The company that can provide them.
And I think like the compounding returns to scale and speed with a efficient model that can it's less than 50 years really. It's like it could be 10, it could be 12, you know what I mean?
I agree.
Yeah.
And again, like I'm not sitting here telling you a guaranteed. Like I would never guarantee anything. I think that's the worst way to look at it. I think the best way to look at it is in a future. Do you think it is more probable that new materials will exist, or do you think it's actually less probable? Do you actually believe that we will still use materials from 1980 in that era in 2100 or whatever? I don't pick your date, 2050.
Yeah.
My answer is no. I think it's very, 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 very probable. The answer is yes, we will use new materials to do that. I'm biased. I'm building a materials company. I acknowledge that bias. I'm not afraid of that bias. But yeah, we think the world's going that way, and that's the bet that we want to make. That's the game we want to play, and that's the world we want to help build. We want to stamp the Radical logo on the Mars base that we send humans to. That's the way that we view it.
Mm-hmm. And I'm curious. I mean, this sort of industry category of an AI accelerated material science company is like a pretty new thing, but there's a bunch of companies in this space. How do you view like the kind of competitive landscape where you guys fit in?
Yeah, great question. It's been amazing to see when we started the company in Jan of 24, so a little over 2 years ago. This is a true story. People won't believe this with the market dynamics today. This is a true story. I did hundreds of like talks with industry and academia and scientists, and the number one pushback was get the vision, new materials, like understand what you're trying to do. Computational side, ICME has been a thing for a couple of years. They were all aware was self-driving labs is a waste of time. Too CapEx intensive. Don't do those things. So hard to build. You're going to automate a science lab? No, you're not. And then you fast forward to today, and there's multiple companies in the space building A lab technology. You have Ginkgo Bioworks reshifting the entire business to A lab technology. You have DeepMind building an A lab because they need data for their models, because they did AlphaFold too, and then they won a Nobel Prize. And a lot of that data, some of the data in that was experimental, of course, in nature. The world today is finally catching up to where we were 2 years ago. And what we realized early on, and we've said this publicly a lot, and yet still people challenge us on it, is we think all the value is in making and selling the material. If you go to the public market today, because that's the only comp that we have, you can go to the private markets too. The value in a material is not in the composition. It's actually not even in the discovery. It's in being able to make it at the largest scale for the best performance, best cost, least supply chain risk, pick your other axis. That is what makes a material valuable. That is what makes C103 valuable in the market today. That is what makes SpaceX's custom alloy SX500 valuable, because they could make it. They didn't come up with a computational theory of a new alloy that would be cool if they could put it in Raptor or wherever else that exists on the Starship. They made it, and then they put it in their product, and they got the performance from it. Materials exist in the physical world. The ground truth of materials is in experiments, is in making them. And for us, that's our biggest differentiation, is we want to sell them. We want to sell material. We don't want to sell it. We'll never sell ML. We don't want to sell ML models. We think most models are going to be open source, honestly, in a couple of years. And dude, maybe quicker than I thought. With the way Claude Code's going and Codex and like where we are with that, I think models are going to be open source. I think every PhD will have access to a fairly decent, if not state-of-the-art model in diffusion. With an MLIP. MLIPs, that's already the case. Allegro, ChargeNet, Ucoformer. There's a bunch of them that you can use today. And we think licensing doesn't capture the value. I think you get reverse engineered because, again, 90% of the value is in the processing of the material. It's not in the IP of the composition that you made. Well, that brings you to the last place that you can be, which is manufacturing and selling materials at scale. And we're really the only company that I'm aware of, and I'm sure others will change. I'm sure others will watch this and quickly say they're doing the same. We're the only ones who are really pursuing that as our core business model. That is what we're doing. That is where we're going. I think a lot of the others are choosing something somewhere in between the first part of that matrix. And we've just never done that. We've just never had interest in doing that. And that's the big difference for us today.
And capturing the highest value of that overall production stack really speaks to the opening point on concurrent engineering. Like Correct. That's the approach you have to have, right?
That's exactly right. If I make an alloy today, I pull something up on the screen here. That's the greatest alloy the world's ever seen. And then I tell you, I can only make 5 grams. You would say, I think, who gives a shit? Like that, I'm super happy you guys made that. Go write a publication on it. I need 20,000 pounds of it to put it in an engine. I pick your application. So yes, to your point, correct. You need to be able to make it at large scale for the right price or for the right performance or for the right other axis that you're trying to solve for. And the only way to do that is to build an interconnected flywheel that goes from discovery to manufacturability. And that's why, and that's where we're going and why we believe in going that way.
So I get the concurrent engineering for value capture across the whole stack and a bit of the tech going in. Yep. So the first place you're going is alloys, but that's really just like the beginning point. In your mind, what would be like the next 2 or whatever like steps, logically speaking, from there?
You mean like in material system?
Yeah, like I would think, okay, like alloys for material strength and aerospace components. Like, is the next place you want to go like new computing substrates? Is it like something?
So That's a very good question. This is the question we have the most fun with as a founding team. I have an incredible scientist on our founding team, Herd Cedar, as I mentioned, and Jorge Calindres is the other founder, and he is ambitious as hell and wicked smart. And when us three get together and say, what should we do next? That is usually a multi-hour whiteboard session on all the opportunities, which is great because as I mentioned at the beginning of this call, everything comes back to materials. A couple areas that are most interesting or that we have seen and kind of are ripe for materials innovation. Semiconductors at large. I cannot today talk about specific areas for a very specific reason with the government, but there's a lot of work in semiconductors that needs to be done. Ceramics are a interesting area that a lot of people talk about next to alloys. They're very similar. They have a lot of cool properties. They're typically done with alloys, like you'll coat with a ceramic coating or something similar. That's interesting. I think polymers generally are super interesting. I talk to Guar about Solugen all the time about how they're thinking about this space, and he's awesome. He's building a great company there as well at Solugen. But they have a big market. Like they end up in so much stuff, right? You got organic stuff in here, you got organic stuff here, and you got organic stuff, in every industry in the world, honestly, plastics in your food containers, etc. So that's a good one. I think last would be we have thoughts on like classes of super exotic materials. Yeah, sure. RTAP is one. There are other thoughts that we have not just RTAP.
That's room temperature, ambient pressure superconductor.
That's correct. Yes.
Yeah.
The holy grail of material science is typically called. And I will say, like, for those watching, ask Claude or ChatGPT what happens if we have RTAP superconductors. That's an awesome wormhole to go down. Wormhole to go down. There are others in that category, like you want to call it a category, that we're excited about, that we think about. We're not doing today, to be clear, but we've thought about. And we have thought when we have more knowledge than anyone else ever has in materials via the amount of experimental data we've collected through our A lab, that will be really possible. Like real quick, this is very random, but we're moving into 45,000 square feet in April of this year. And on the left-hand side here, these are two of the labs in this new building that we're building. So it's this whole building right here that we're moving into. And the governor and the state's been super supportive of this. And the reason I'm bringing this up and talking about this is we want to build out a lot of systems here. And we want to really scale that experimental data. So today, we're targeting 700 experiments per week. That's one system. If you do that out across like 7 systems or call it 10 systems, you'll start to push 330,000 experiments per year. That's more than half of the experiments every scientist in North America will conduct this year. It's like a little over half. You can double that number again and then do all of the experiments that scientists have conducted in North America this year. In our opinion, that'll be the smartest scientist in the world and be the best chance of getting an AGI for science.
That's awesome. And it's really like you dial in the self-driving lab, module, and then just like place it down, like stamp it everywhere, like, have 100 stations running simultaneously.
Correct.
In some sense.
That's exactly right. Yep.
And there's your self-driving fleet.
There's a self-driving fleet. There is the iPad on the beach, and you're just Tony Starking yourself across the board. And it's doable, right? Like classic startups, but the 0 to 1 is so much harder than the 10 to 100. We have 11 tools today that are, one of them is not automated, but 10 tools that are automated. That was hard to get to, dude. We got kicked in the teeth a lot and just kept moving. We're less worried about the 10 to 100. I mean, like there's a lot of work to do. I don't mean to diminish the work. There's a ton of work to do, but the 0 to 11 there was a lot of novel invention in the 0 to 11. things that I know for a fact the industry has not thought about yet because we didn't think about them, and we now know them. And when we think about automating a system, those things are top of mind. So we actually feel like, oh, now when we can turn on the jets, when we can start just crushing the 100, 200, 300, 1,000 connected tools, you're going to get close to AGI, and then expand that further. If you want to get crazy, what about sending these to Mars in boxes? What about sending to the moon? Sending them past that. Not solar panels on Mars. Martian soil. Not with
well, so I'm
soil.
curious there. I mean, let's now get let's go there, to the sci-fi
Let's
future that we're all building, right? So you have the robotic the science factory, basically, like you're mass producing experimental results. But then also for the production, there's probably this other part, which is like the auto forge or something like that.
Mm-hmm.
And that's maybe the thing you ship to the moon, because you need to produce them in situ using local resources at scale.
Correct.
Instead of you ship the factory, not everything it builds.
Exactly right. And I think solar is a perfect example here. I remember I was listening to a podcast. I think it was Cognitive Revolution, but I'm not sure. But shout out to the Cognitive Revolution team. They're great. Where he said, one of Blue Origin's problems is energy. You're not going to carry solar panels to Mars. That would be crazy. And by the way, they're not even efficient. So nor are they built for up there, probably 24/7. They probably can do different things. You don't have to worry about space as much, etc. So what do? Well, you have to figure out a way to make photovoltaics with the Martian soil. How do you do that? Well, you need a research lab, probably one that's autonomous. And then to your point, once you discover that, what do? You don't send humans to then go build them out. No, you got to make it autonomously as well. And so, yes, is the direct answer to your question. You're 100% correct. You have to begin doing that. And by the way, there are already companies thinking about that. They're just thinking about it at the application layer. They haven't taken that step into raw material manufacturing. It's more like I'm going to print a missile body, or I'm going to print turbines or nose cones for rocket engines, like very specific things like that. One jump from that is well, what are you printing with? Materials. How are you printing them? Some manufacturing technique. That's where we start to blend into our world. So we're thinking about this, and we're not there yet. We're young yet. We haven't been able to tackle that yet. We had to get discovery solved first, which we've done now. I can confirm today that we have results from the lab. It's not theory. We have new results that we'll release in the future. We're super excited about releasing, but it works. It works. And thinking about how to take that to the large scale is something we think about all the time.
Mm-hmm. What's your estimate of how much of the, engineering technical risk lies in we can synthesize small samples reliably for the purpose of characteristics metrology to now need to batch produce this at is that a valley of death in the material science?
Yes, it is.
Okay.
And it's a great question. And I don't have an exact percentage for you. I have the worst answer, which is I don't know.
Yeah.
I'll tell you this. I do know this. The normal process today has you start with zero information. Whatever you get from the patent holder and or the discoverer of something, right? I made it this way, and here's the structure, composition, etc. What we'll have will be a very rich data set in probably, call it 50,000, 100,000 alloys at all different temperatures, all different pressures, all different annealing rates, all different manufacturing light scale manufacturing techniques, that we have a corpus of ranges and information, ranges on that information that we can use to think about where to go next. And I always use baking a cookie as a good example. Now, if you bake one cookie, you're like, great, it's amazing. My wife is like, great cookie. She'll never tell me that, but she makes much better cookies than I do. That's not the same as making 1,000 a day at a bakery, though, right? You're not going to say, oh, turn the oven to 1,000 because we're doing 1,000 now.
Yeah, that's
You're
right.
gonna, you're gonna burn the cookies off. You might go to 450 versus 350. There might be like variation, but you're gonna know like where you're gonna need to be for the cookie to, for
Mm.
the dough to rise and the chocolate chips to melt. That's where we're gonna start, right? Is like we've captured the 100,000 tries of making the perfect cookie. So yeah, go into 1,000. You're gonna optimize temp, optimize position in the oven, optimize how much you stir it before the dough and the chocolate chips you stir it before or whatever, how much you leave it overnight to proof. But we have like an inkling on where we should go with those things. We think that's one of the huge values of capturing the data.
That makes me think, actually, it's like part of that valley of death is an artifact of the difficulty of translating sort of individual science intuition to the manufacturing facility or metallurgical engineers. Whereas you guys have this this huge corpus of information and now machine understanding of like what is the trade-off space of all of our process and control variables in synthesizing at small volume. So when you go to the large scale, it's like, oh, it's likely this. It's like a temperature asymmetry. It's some gas impurity. Like you kind of have information on how to like build that or cross that gap, I guess, essentially. So you're building up the competency here, but as you build that, it kind of becomes less and less of a valley.
Correct. And becomes more and more of a moat because it's harder to cross.
I'm gonna steal that, dude. Turning valleys into moats. That's hilarious.
Oh, come on, give me. You gotta give me a little bit of that. Give me like 10% of that love.
I'll reference that. I'll cite that. Yeah.
Because you can't fake experiments, and you can simulate them. Sure, we do that today. Can't fake them. You got to run them. You have to capture the raw data. And so the more you cross it, the valley, the deeper it becomes for other people to go cross.
That's right. That's right. Totally. That's awesome. I love that. Okay, so you guys solve the 0 to 11 problem. You're building up this new factory space. I think you guys are all in New York City or like the surrounding area.
All in New York City right now. This is in the Brooklyn Navy Yard in New York City, so right across from Manhattan. Yep. Right next to where we were at Deep Tech New York.
Yeah, New Lab. Yep.
So right next to New Lab. It's 45,000 usable square feet. Super excited by that. Huge shout out to Economic State or Empire State Development, who gave us a grant. It's been publicly released now by the governor, et cetera, to help do this. And we're all in New York today because it's just really important. Look, I'm not going to bullshit you. We're psychotic about the culture. We're okay that we're psychotic about the culture. We're not afraid that that's the case. We are ruthless about who we bring in and why. And we're all in person. We don't do remote work. I don't believe in remote work. I don't like remote work. Will we have other offices in the future? Of course, we're not naive. We know how companies operate. But today, in this 0 to 1 phase, in this like getting that full flywheel running, it was very, very important everyone was in one spot. One of our biggest assets is speed. We move so fast, faster than startups say they move fast because everyone's here and everyone is constantly focused on solving the biggest problem in front of us. And I always tell people I love when I interview people because I always ask them, look, are you looking for a job? And if they say yes to that, I'm like, no reason to continue the interview. Not a fit. This is not the place for you. But if you're looking for a mission, then we should.
Yes.
Because everyone that's coming here, everyone that's came here is here for that. They're here for the mission. They can honestly go get a job anywhere. It's about solving the materials bottleneck that we're facing today. And we have 3 core principles when we look for talent. First principle, analysis, quick decision, 51% rule from SpaceX. And you really, you have to have a ridiculous amount of tenacity. Because when you're trying to build new technology that doesn't exist, it fails a lot. Not a lot. 99.9% of the time, it blows up in your face. And so you have to be able to ask why. Why is our favorite question. We first principle everything. We actually have people first principle physics sometimes. They're physicists usually, not me. But you have to be able to make quick decisions. I love SpaceX's 51% rule. I love it. I love that. And it is so true that by debating the time it'll take to get the 90% confidence, you could have already made a decision, been wrong on that decision, and made another one, and been 2 steps ahead of the single one. And then tenacity, because those 2 things will cause you to fail, and you just have to continually be focused on the mission. If it's a job, that'll be demotivating, and you'll quit because it doesn't work. If it's a mission and you want to change the world and leave an impact, you'll keep pushing. There's a lot of companies that say they're going to impact the world. I was an investor for 3 years. I've heard all of the pitches on it. There are very few that say the result, the output of the company impacts every single person in the human race. That is true of Radical AI.
Yeah.
They might be different at different times.
I wholly agree.
At large, it's true. Yeah.
Yeah. If like me as like science tech dude, if I could just crank a knob on one field for all of the downstream impacts, it would be materials. 100%.
Agreed.
You'd have supercomputers, fusion, like indestructible rockets, like everything.
Yeah, could you imagine? Can you like how excited? I'm so fired up, dude, because I don't know how people aren't like. I can't even sleep at night right now. I'm just like I just like the future is evolving and it's so exciting because the world you just painted. Like we're gonna be Andrew, we're gonna be hanging out at like the cafe on Mars, watching the science robots like make the thing.
Right.
There's some fake burger that is like 3D printed. I don't fucking know. Like whatever's coming. Like that to me, that is so exciting. That's the why. And the technology supports this becoming a reality. That we're in this period of time where we have no option but to invent the technology. Either stagnate or accelerate. And we're going to choose accelerate every time. And God, I don't know, it fires me up, dude. I'm sorry, but it fires me up like of the world we're building and the world we're all living in. And yeah, you just get so much inspiration from all the stuff everyone's doing. Going to be a good future. We have a very positive future ahead of us. It is going to be one that is fruitful and exciting and innovative and fun and just straight up fun. So it's going to be a good
man. That is, I love, like, just you encapsulated exactly my worldview right there. Like, people don't realize how good it's going to get. Everyone's like, oh, everything's going to kill. Like, no, the doom narratives are just broken.
I completely agree.
Yeah, we got to just build the better tomorrow. So just before I let you go, like, any quick shout outs? Are you looking to hire? Are you looking for, like, while we have the audience here, anything?
I thought I had sorry, I just accidentally did that. I thought I had a slide on the mission.
It's all good.
If you're bored in what you're doing right now, you're doing the wrong thing. And the opportunity to change that can happen today. And if you want to change that in a way that, as I just said, scales into impacting billions of people over the long run, call me. Because the people that we're looking for are not normal people. They are people that are obsessed with building a better future and are obsessed with solving hard problems and are obsessed with charting into the unknown, not being afraid to step out off the plank and like see what happens and just dive in. If that's you, like, please let me know. And then another area that I'm interested in is if you're building an organization that wants to partake in the future of materials, let us know. We can't respond to everyone today. We don't have the bandwidth to do so just yet. We're working on it, not yet. But if there are problems that you're facing that are material in nature, by the way, there are problems you're facing that are material in nature, please reach out. We like working with innovators who want to build concurrent engineered approaches. And so if that's you, like, give us a holler. We'd love to talk to you about it. And then I think lastly, do not be doom and gloom about the future. Andrew just said it perfectly. The future that will evolve over the next 10 to 50 years is unimaginable, literally. Like, I don't think we can predict what 50 years looks like. We can have an idea only we can predict it. You should be fired up and excited by that. And so my parting message would be, if you're not, call me. And if you are, call me, because we could probably work together. And so in short, call me. All seriousness, if you want to work on a hard charging, fast paced mission that's psychotic in nature, we'll take up one with, I'll reward you with, we'll give you a reward that you can't get anywhere else. Come to that. We are hiring aggressively. We're scaling every discipline right now, and we love to talk.
That's awesome, man. That fires me up. I'm like, why should I should join? Like, I'm gonna quit.
What are you up to next? I was about.
What
to
am I
ask
doing? Yeah, what the hell?
New York. Come look at the lab.
I should. Yeah. Well, I'll be there soon for Deep Tech Week, and you should come.
Oh
hang.
Yeah, fantastic. We'll hang out for sure. Shoot me a text. You should also come check out the lab in person.
I would love to. That sounds great, man.
Yeah.
Thanks for your time today. Appreciate it.
Thanks for having me, Andrew.
Okay, we'll talk again. All right, see you, man.
See you.